Hello everyone. Now in this video we study about the Booth's algorithm. So first we see the flowchart of the Booth's algorithm. So first we start to solve the example. In this a is equal to 0 means a means the accumulator is equal to 0 initially. Then q1 is equal to 0, m for the multiplicand, q for the multiplier and n for the number of bits. So in this, if q 0 and q minus 1 is 0 1, then we do a is equal to a plus b. We add multiplicand in the accumulator and result store in the accumulator. When q minus is 1 0, that time a is equal to a minus 1, and if q and q minus 1 is equal to 0 0 or 1 1 means both the bits are the same, that time we perform arithmetic right shift, and then n is equal to n minus 1, n is equal to 0, and when n is equal to 0, that time we end the process. So how this flowchart is work, we see with the help of the example. So we use Booth's algorithm for the multiply the two numbers. So let's we see how it work. So let's suppose the given example is minus 9 into 13. So as I say, we use Booth's algorithm for the multiply the two numbers. So first, this is the form of m into q. So m for the multiplicand and q for the multiplier. So here now m is equal to minus 9 and q is equal to 13. So normally how we write 9? 9 is equal to 0 1 0 0 1. So in this example our n is equal to 5. So we write all the bits in 5's group. So 1 2 3 4 and 5. So normally 9 is in the form of binary is 0 1 0 0 1, but our multiplicand is minus 9, not 9. So first, now we find the first complement of the 9. So first complement of 9 is equal to, change the bits. If 0 is present, then it converted into 1, and 1 is present, then it converted into a 0. So this is the first complement. When we find out any number, then now 0 is converted into 1, so 1 0 1 1 0. So this is the first complement. Now we find out the second complement, and when we find out the second complement means 2's complement, that time we find out the minus 9. So when we want to find out the positive number to negative numbers, that time we do 2's complement and we convert the sign from positive to negative. So now 2's complement of minus 9 is equal to, how we convert the 1's complement into 2's complement is add 1 in the first complement. So 0 1 1, this 1 1 0 1 as it is. So now this is our minus 9. So when we convert positive number to negative number in a binary form, that time find out the 2's complement. For that, first find out the 1's complement, then add 1 in the 1's complement and find out the 2's complement, which is our negative number. And q is equal to 13. So 13 in the binary form we write 0 1 1 0 1. So this is our m, and if we want minus m, then we do minus of minus 9, because minus 9 is m and this minus is here. So this minus in bracket, the m's value is minus 9. So this is 9. and the binary of 9 is 0 1 0 0 1. So now we find out m minus m q, and if minus q is present then we find out minus q also, but in our example only q, so no need to find out the minus q. If we want to find out minus q, again same procedure we follow. First we find out 1's complement, then we find out 2's complement, and this is the minus of q. So first in our flowchart we see initially a is equal to 0 and q is present in given in our example, so no any issue. So a, first we write here a, here q, and here q minus 1. This is the operation. So initially our a is 0 0 0 0, these 5 bits of a, and q is our 0 1 1 0 1, and also we see initially q minus 1 is equal to 0, means a is equal to 0, q is given in our question, and q minus 1 is equal to 0. So we want q and q minus 1, so q minus 1 is 0, and q's last bit means rightmost bit which is present right here, this is the q and q minus 1, so 1 and 0. And we see in our flowchart of the Booth's algorithm, when 1 and 0 is come, then that time we perform the operation a is equal to a minus 1. So one trick I want to say, if first number is 1 is present, so do a minus m, and if 0 is present then a plus m. For our simplicity, for so a is equal to a minus m, so we find out the value of minus m, so directly we add value of minus m into a. So what is the value of minus m? Minus m's value is 9, which is 0 1 0 0 1. We not perform minus because many times we do many mistakes in the subtraction of the binary numbers, so we perform addition quickly, so for that we find out minus m and directly add them, so we get the answer of a minus m. So 0 1 1 0 0 0 0 plus 0 0 0 plus 1 1 and 0 plus 0 0, and we see if after the performing the operation we do right shift of the given bits. So first we write all the q as it is, q1, and this 0 also we write. Now after operation we do right shifting, so here this 0 is go now in the below of 1, and this 0 right also here also. So now all the bits are do right shift 0. Now this 1 is go here, and in this way we do all the right shifts of the bits. I hope all you get idea how we do operations and what steps we follow here. So now taking your mind, if 5-bit number is given, then we find out 5 steps. This is our first steps. So in this way find out the 5 steps for the 5 number bits, and last 5th steps we get the answer of our question. Now the second step, write all the output of the first step is our now input for the second step. 0 1 0 1 1 0 and this 1. So first we find out q and q minus 1. So now q minus 1 is 1 and q is also no, here q is 0 and q minus 1 is 1. So this is 0 1. So as I say, for quickly do operation, what see which number is come front. If 1 is present, then directly do a minus m, and if 0 is come, then a is equal to a plus m. This is the one trick to get quick operation. So we know the m's value. This plus 1 add into the a. So what is the value of m is 1011. So 10111. So we add them. So 0 1 1, 1 plus 1 0, carry 1, 1 plus 1 0, carry 1 is go here. So 1 plus 1 0, 0 plus 1 is 1, and this 1 carry go from here, this 0 to 1. So now 1 plus 0 1, and 1 plus 0 is 1, means 1 plus 0 is 1. Now again 0 plus 1 is 1, and this q write as it is, and this. Now after performing the operation, do right shifter. So this one right here, and this is the right shift of 1. Now remaining all are the do right shift 0. See here, we only do right shifting of each bit. So now the output of the second step is the input of the third step. So this 1 1 1 1 0 and 1 1 0 1 1 0. Now in third step, q and q minus is 0 1 1 0. Again the operation now we perform is a is equal to a minus m, because 1 is come here. Otherwise we refer the flow chart, but refer the flow chart and then decide which operation we do. This is the too much complicated process. So I use here trick. If 1 is come, then I directly perform minus m, and if 0 is come, then I do addition of the accumulator and the m. Now value of minus m is 0 1 0 0 1. So now we add, then we get 0 plus 1 1, 1 plus 0 1, 1 plus 0 1, 1 1 0, carry 1, 1 plus 1 0, and carry 1 is come here, but 1 plus 1 0, 0 plus 0 0. Here not put carry here because we want 5 number bit, so don't consider the carry bit. So 0 q right as it is. Now we perform right shifting. So this 0 and this 0. Now 0 1 1 1. We only do here right shifting of all bits. So in now fourth step, our q minus 1 and q is same 1 1, and when q and q minus 1 is same, then directly we perform right shifting directly. So this 0, this 0 0 1. Now we come for the last step. 1. Now our q and q minus is 0 and 1. This q and this q minus 1. So 0 1. Again the operation we perform is a is equal to a plus m. So the value of m is 0 1 0 0 1. then we do addition, add them. Then 1 1 0 carry 1 1 0 1, then 0 plus 0 0 0 plus 1 1, and this 0, and all are the remaining right here as it is. Now we do right shifting of each bit. So this 0 0 1 0 1 0 and 0. Now in this fifth step we get the answer, but this answer is come in a positive integer. So we want negative answer because we know when we multiply minus 9 into 13, then we get minus answer. So for the result we want minus, so we perform 2's complement to convert the given answer into the negative. So take in your mind, if when we want minus answer, that time 2's complement we do in the last step, and if the answer is come positive, that time no need to perform 2's complement directly, which is the result of the fifth step. This is our result. So 2's complement of the result, for that first we find out 1's complement. 1's complement. So 1's complement only we consider a and q, not q minus 1. This is q minus 1, this is q, and this is a. We want to find out answer of a into q, means we consider a and q, not consider q minus 1 in the result. So the bits are 1 1 1 0 0 0 1 0 1 1 0, and sorry, this is not considered because this is q minus 1. So now 1's complement is 0 0 0 1 1 1 0 1 0 0, and 2's complement, for that add 1 in the result. So 0 plus 1 1 0, remaining all are the bits is the same. Now we check our answer is correct or not. This is now our final answer of minus 9 into 13. So normally we know minus 9 into 13 is equal to minus 117. So we check the same answer is come or not. So 1 2, let we count. So 1 plus 4 5, 5 plus 16, 16 plus 32 and 64. So the answer is come 117, and we do 1's complement, so this minus is also come here. So we find out the correct answer of the question. At the end we prove also here. So this 0 0 0 1 1 1 0 1 0 1 we write in the form of. So in this way we prove also, means 2 raised to 9, 0 into 2 raised to 9, because total 10 bits are the present in the given equation, given binary number. So 0 into 2 raised to 9 plus 0 into 2 raised to 8. So in this way we go from 0 into 2 raised to 9 to 1 into 2 raised to 0, and when we find out the result, then we get 117, and we find out complement, so this is also minus 117. I hope you all get idea about how to find out the Booth's algorithm for the multiplication. Thank you.